In the early part of the 20th century, Gilbert Lewis developed a theory of bonding that is particularly relevant to organic chemistry. And what Lewis's theory stated was that covalent bonds result when two atoms share a pair or pairs of valence electrons, and they do so in order to achieve a noble gas electronic configuration. Now, for organic compounds, this is commonly referred to as the octet rule, in that each atom in the organic compound will have 8 electrons. All right, we can look at a simple example, and that is the formation of the H2 molecule from 2 hydrogen atoms. Now, each hydrogen atom has a single electron in the 1s orbital, and these orbitals will overlap to form a bond, and that bond now contains 2 electrons. Right, we can look at the energetics of this process of 2 hydrogen atoms forming H2 on the right. So at the top here, we have the 2 hydrogen atoms. Okay, and the arrows represent the electrons, and we use these arrows because this represents the spin of the electrons. So just very briefly, all subatomic particles can be described by 4 quantum numbers. The 4th is known as the spin quantum number, and for electrons, this can either be plus or minus 1/2. So in this particular case, both electrons are aligned, so this would be plus 1/2. Now, in order to form a bond, one of these electrons will have to flip its spin so that it can pair with the other electrons. And so to form H2, we now draw the paired electrons with opposite spins. So one would be plus 1/2 and the other would be minus 1/2. Now, when this occurs, this is energetically favorable by 436 kilojoules per mole. So H2 is 436 kilojoules per mole more stable than 2 hydrogen atoms. And this is because in H2, each hydrogen atom now has a noble gas configuration of helium. Okay, and so it is now its valence shell is filled. Right, we can look at the energetics slightly differently on the next slide. So here, this is a plot of interatomic distance versus energy. So out here on the plot, we have the 2 hydrogen atoms. So the 2 hydrogen atoms distance can go from a distance where there is no bond, so out to infinity. But as we bring these 2 hydrogen atoms closer together, they start to form a bond because their orbitals are going to overlap. And then they form the ideal distance, and so this is the bond length of about 0.74 angstroms, so that's the distance between the nuclei. But if you try to compress them more, try to bring those 2 nuclei closer together, Coulombic repulsion takes over, and so the energy starts to go back up. And so this value of 0.74 is the idealized bond length between the 2 hydrogen nuclei. Okay, now one thing to point out is that bonds are not static. They actually behave sort of like a spring, and so they oscillate back and forth about this equilibrium distance. Okay, in the center of the slide, we have some information about the 3 main subatomic particles of an atom. That is a proton, neutron, an electron. And I think you all already know that the protons carry a positive charge, neutrons are neutral, and electrons have a negative charge. We also have the mass of each of these particles, and the important thing to note here is that electrons are about 5,000 times lighter than protons and neutrons. So the mass of an atom, and consequently a molecule, is largely due to the protons and the neutrons in the nuclei. Now the electrons circle the nuclei, and while they have a negligible mass, the electron clouds around the nuclei actually are going to make up most of the volume of an atom or a molecule. All right, finally, let's look at the bonding of some elements in row 2, and these will actually serve as examples of the octet rule. Okay, so on the left, we have the formation of molecular fluorine, F2, from 2 fluorine atoms. Okay, so each fluorine atom has an unpaired electron and 3 pairs of electrons. Okay, so fluorine, the 2 fluorine atoms will come together, and the orbitals in which those unpaired electrons reside will overlap now to form a covalent bond between the 2 fluorines. And what you can see here is that each fluorine now is in possession of 8 valence electrons, 3 pairs of electrons each fluorine atom has for itself, and it's going to share a pair of electrons. Okay, so each fluorine atom now has the electronic configuration of the noble gas neon, and its valence shell is filled. Right, on the right, we have the formation of the methane molecule, CH4, from a carbon atom and 4 hydrogen atoms. Okay, so what happens here is that the orbitals, that the unpaired electrons in carbon will overlap with the 1s orbital that contains the unpaired electron of the hydrogens. Okay, so this happens 4 times, and so now we get 4 CH bonds. Each CH bond now shares a pair of electrons. So carbon now has 8 electrons in its valence shell, and so it has the noble gas electronic configuration of of neon, and each hydrogen atom has 2 electrons, and it has the noble gas electronic configuration of helium. Okay, now drawing structures of even modest complexity and including all 8 electrons around all the atoms will be very cumbersome, and so we have developed shorthand methods for doing this. First, what you will often see is electrons not participating in bonding are omitted, but they're understood to be there. The other important part of the shorthand is that bonds are represented by a line between the 2 atoms. So this would be the representation of the F2 molecule, and that line represents 2 electrons. Okay, so methane would be drawn as such, where there is a line representing 2 electrons between the carbon and each of the 4 hydrogen atoms. All right, now when an atom deviates from this octet rule, this closed valence shell, then this usually means that it must have a formal positive or a formal negative charge, and that will be discussed in the next section.